Welcome to part one of Igneous Rocks and Processes. We kind of started this discussion a little bit before break, but now we're going to get more in depth. So the best way to go on this is to start with the rock cycle. We've talked about sedimentary rocks, so that's kind of the top part of the rock cycle where rocks get eroded and sediments moved from the coast to the shoreline, and so that's where that is. Now we're going to talk about really something that happens before you can even have erosion is you have to make a rock first. So the earliest rocks, the oldest rocks on the planet, the first rocks to form would have been igneous rocks. And igneous rocks are the rocks that form from the solidification of molten rock. Now, if you look at this slide, you'll notice there's a lovely picture from your book of a volcano erupting there. And so we want to talk a little bit about how this happens and where it happens and the kind of rocks that you would find. So what happens is we start out with molten rock, and when rock is melted, it is melted because it is at a very high temperature and the molecules and atoms are moving too quickly to assemble into mineral crystals. So in order to form an igneous rock, we're going to have to lower the temperature of that magma. And as we lower the temperature, the molecular motion slows down. And once that starts to slow down, mineral crystals can form. Now, this will take place at a series of temperatures. So if you think about minerals, every mineral has its own set of physical properties. One of those physical properties is the temperature at which it melts, or the opposite side of the same thing is where it forms a solid crystal. So different mineral crystals will form at different temperatures. Way back when we looked at minerals, we looked at briefly the Bowen's reaction series, and that shows you the temperature at which different mineral crystals form. And we'll mention that again as we go through this, so you can look it up in your textbook, but that's definitely something to think about. So bonding takes place and mineral crystals form, and this happens in one of two places. The obvious place, the place that we see, is what we call extrusive, or outside of a volcano. So the first identification of igneous rocks happened when geologists were basically watching volcanoes erupt and noticed the rocks that cooled and solidified outside of a volcano. But of course, that leads you to think, well, what happens inside a volcano? What about the molten rocks that never make it to the surface, that cool and solidify under the ground? And those are the ones that we call the intrusive igneous rocks, and they are also called plutonic. So for Pluto, the god of the underworld, as opposed to Vulcan, the god of the forge and fire. So that's intrusive versus extrusive. Because the extrusive ones are the easiest ones to see, and the first rocks that geologists looked at closely and thought about the formation, we will talk about the extrusive rocks first, and that's how we'll finish this particular slide presentation. So extrusive igneous rock forms when molten rock cools at the surface. So when it's extruded from the ground and lays on the surface, it cools and solidifies. So let's take a look at some of the materials that come out of a volcano. The first material would be pyroclastic material. Pyro means fire, and you probably remember the term clastic from sedimentary rocks. That refers to pieces of rock. So this is fiery pieces of rock. And we have two general groups that we put these into. The ash, the blocks, and the bombs are the big chunks that kind of get thrown up into the air and fall down. And in certain circumstances, they can become part of what we call a pyroclastic flow. And this happens because that cloud of ash is actually very dense and heavy, and gravity can pull it down the side of a volcano, pyroclastic flows can travel at 60 or 70 miles an hour down the side of a volcano. And they look kind of like a fluid flow, but they're actually made up of hot gas and ash. So the pictures we have here show you a cloud of pyroclastic materials on the right. So that would be mostly ash, but also falling out of that would be blocks and bombs. Blocks are just solid chunks of rock, and bombs are the picture on the left. This is molten rock that cools and solidifies on its way down in the air. And so in this case, you'll notice it has a kind of a streamlined shape. So that is pyroclastics. The pyroclastic deposits are what we call tuff deposits. You can see two examples here. I took these pictures on the island of Oahu in Hawaii, which is an extinct volcano. On the left, you'll notice that ash deposit has blocks of material in it that are fairly sizable. So we've got some pyroclastic blocks mixed in with the ash. And the deposit on the right is a finer material, and you can see the layers of ash in there, which indicate multiple eruptive cycles to produce those multiple layers of ash. And some of the material down at the bottom is quite fine. It's the size of maybe dust. And you'll notice there are a few layers moving up toward the top that are a little bit larger, maybe the size of sand. So we actually use we use the same size terms that we would with sedimentary clastic rocks. So that's our pyroclastic deposits. They're called tuff. We also get molten rock coming out of the ground, and this is a picture that I took on the big island of Hawaii. The picture on the left is just a close-up of what you see on the right a little bit farther out. This is a volcanic vent. That hole is a place where lava came out of the ground, and it was splashed around that vent, and that's why we have a pile of material there in that left-hand photo. That is cooled and solidified molten rock. If we look a little further, the picture on the upper left is from your textbook. It shows an active lava flow. I did not have the good fortune to see an active lava flow. However, on the right, you can see what that would look like after it cools. And I took that picture on the big island of Hawaii. That's a lava flow that had formed, I think, 20 or 30 years earlier and spread down the hill and across the landscape. On the lower left, you'll notice a place where the road cuts through one of these lava flows, and you can see multiple layers within the lava flow. Initially, some people thought that this just was small lava flows building one on top of the other, but as geologists have observed the formation of lava flows, what they find actually happens is that the outside or top of the lava flow solidifies, and then more lava comes in. So the layers that you see here were actually layers filling in this lava flow from the bottom, and they would have kind of expanded the top as they pushed their way in. And then on the right-hand side, on the bottom, you'll see the top of one of these lava flows. This is what we call a Pahoehoe lava flow. Pahoehoe is the type of lava flow that has kind of a smooth surface with what's called a ropey texture. So you could walk on that barefoot, you'd be fine. The other type of lava flow I don't have a picture of is an lava flow. It has a very rough surface on top and would be very difficult to walk on, at least barefoot. If you walk on it with your shoes on, it'll actually tear up your shoes. So people generally avoid walking on lava flows. So the next picture is a picture of what happens when lava erupts under the water. What happens in that case is we get this kind of bubbles-shaped lava flow instead of the layers you saw in the previous slide. You'll notice that the feet of my children here, there are a bunch of little kind of globs of material, lighter colors within little dark bands. And then on the right-hand side, you can see one of these, what we call pillows, in cross-section, kind of up close. And what happens in this case, when lava erupts under the water, the molten rock comes in from the bottom. It immediately solidifies on top when it hits the water, and then that bubble can fill in with lava. And when it gets too big, the lava will come out and make another one of those bubbles, which will then fill in. And the end result is what you see on the left, which is instead of a big flow, it's a bunch of these bubbles stacked on top of each other that we call pillow lavas. So this isn't something that you'd see at the surface. You'd have to dive under the water to see it. And some people have made videos of those. If you search online on YouTube, for example, you can find videos of pillow lavas. This is the top of Kilauea volcano on the Big Island of Hawaii, and you can see gas coming out of the top of the volcano. And the other thing you might note here is that there's a big crater there kind of in the middle that the steam is coming out of, and so that is a large caldera at the top of Kilauea volcano. And the gas coming out can be anything from something as benign as water vapor to things that are more damaging, such as hydrogen sulfide, which combines with the water to make sulfuric acid. So when I went to the Big Island of Hawaii, downwind from this crater was closed to the public because of the danger posed by the gases coming out. So we'll look at a few other pictures here. This is a lava flow picture that I took on the Big Island of Hawaii. It kind of shows you what happens to the gas that's in the lava as the lava cools. You'll notice at the bottom of this flow, there are no bubbles because they were rising up toward the top as the molten rock cooled. Some of them coalesced and made a few large bubbles that got stuck when the lava flow cooled. So we see those in the middle, and then most of the gas made its way to the top where you can see many small bubbles there. So that's kind of how the gas ends up affecting the way the lava flow looks. Some other things that are associated with volcanoes, a lahar, which we talked about in the lab exercise that we did before break. This is just a mud flow made of ash that usually forms when the heat melts the snow on top of a volcano, and then it can flow a very long distance from the volcano. So it's basically forms from a combination of ash that's already on the volcano and meltwater from a glacier that might be on the volcano. And so these can actually occur without an eruption if a large amount of heat is given off, enough to melt that snow. And last but not least, this is a short table, and you can refer to the information on here is actually in your textbook. This is just sort of a summary that I created. And it relates the type of eruption to the composition of molten rock that we would find in the erupting lava. Felsic lavas tend to have a very high silica content. They're very sticky. We get more explosive eruptions. And mafic lavas, because they have less silica, they have fewer of those little tetrahedra. They're much more fluid lavas. They have low viscosity, and we get more lava flows. The picture you see there is a mafic lava flow. And last but not least, we have our different types of volcanoes, and I'm kind of running out of time on the video here. The shield volcano in the lower right is made mostly of lava flows. The cinder cone in the lower left is made mostly of pyroclastic material, and the volcano in the upper right, which is kind of our classic volcano form, is a composite volcano. What happens during the eruption is it switches back and forth between pyroclastic and lava. And so the reason that it's called a composite volcano is because that structure is a combination of ashfall, which gives it the steep sides, which then gets covered with lava, which maintains the shape and allows you to build a much larger volcano. So that's it for the first half of the slideshow.